Okay, now that we have a little basis for what the VSEPR model is and the general shapes that both the electron domain geometry and the molecular geometry can adopt, let's now see the relationship between those. So when your central atom in a Lewis structure or whatever structure you draw has one or more lone pairs, right? So this is critical now. When we have lone pairs on the central atom, the electron domain geometry and the molecular geometry are not going to be the same. Okay, so what I mean by that is if I have a molecule like ozone, for instance. So this is O3, ozone. If I were to draw the Lewis structure for it, okay, we have our central O in this case. We're going to have a single bond to an O on the right, double bond to an O on the left. Okay, so I focus on my central O. There it is. There's a total of 3 electron domains: a double bond, single bond, and a lone pair. Okay, so my electron domain, the number of electron domains is 3. And according to the VSEPR model, the electron domain geometry will be trigonal planar. Okay, so I can draw that shape. I know what the trigonal plane looks like. So there's my O. I have a double bond to an O on one side, single bond to an O on the other. I'm going to stick my lone pairs around to make them happy. And then on this O in the center here, I have my lone pair on top. Okay, so if I were to just highlight sort of how these electron groups are oriented, okay, they do kind of look like a triangle. Okay, that's your trigonal plane. That's my electron domain geometry. Now, when I look at the molecular geometry, okay, and this is where it can be slightly confusing. So we're going to slow down here and make sure that we understand this. My electron domain geometry is trigonal planar. When I look at the molecular geometry, all I look at are just the atoms and how they are connected. So not the lone pairs, if there are any, on the central atom. Okay, so now if I look at my molecular geometry, all I'm looking at are how the atoms are connected. So in the case of ozone, I have an O connected to this O, and connected to that central O, I have my other O to the left. So that shape then of the atoms, how they are connected to each other, is not a trigonal planar shape. It is actually bent. And that will be the shape of the ozone molecule. But in order to come up with this shape, we first of all have to know how many electron domains are around the central atom. They're going to have a particular electron geometry. And then we just look at the atoms connected to each other. How are they oriented relative to each other? That is the molecular geometry. Okay, this is going to be the steps for every single molecule where you have to determine the shape of it. You need to first of all start with the electron geometry, and then we can come up with the molecular geometry at the end. Okay, so molecular geometry for ozone will be bent. If we take a look at other examples where we have now more than 3 electron domains around the central atom. So for instance, in the case of having, let's do ammonia as another example. So NH3, okay, if I were to draw the Lewis structure for NH3, you would see that it looks like this. And 3 H's in a lone pair. Okay, so my number of electron domains, and again, it's just around the central atom, the N in this case, number of electron domains around it, I have a single bond, another single bond, another single bond, and a lone pair. So I have 4 electron domains. Okay, so based on that, if I have 4 electron domains, according to what we talked about before, my electron geometry then, electron domain geometry will be tetrahedral. So now I can draw that electron geometry. So I have my N, and I have my 3 H's. Okay, and then I have my lone pair up here. So that's not a bond, that's actually a lone pair that's on top, right? Those are my 4 electron groups arranged in that tetrahedral shape. Now, when I look at my molecular shape or molecular geometry, I just look at the atoms. Okay, so in this case, I have hydrogen, a nitrogen, hydrogen, and then another hydrogen here. So this is the shape I'm looking at. And this shape is not tetrahedral. This is actually a shape called a trigonal. And it's not planar because it's not flat, right? It kind of looks like a tripod. The technical name for a tripod is a trigonal pyramid. So it's trigonal pyramidal would be the molecular geometry for NH3. I can only deduce that based on my electron group geometry. If I take this one step further, if I were to draw the structure for water, for example, so H2O, okay, my Lewis structure will look something like this. Okay, so now again, number of electron domains around the central O will be 4. Okay, so again, we just look at the central atom, and I have single bond, lone pair, lone pair. So those are my 4 electron domains. So then my electron domain geometry will be tetrahedral. So those 4 things will arrange themselves in that tetrahedral arrangement. So I can draw my tetrahedron again. Okay, and I have 2 H's attached to the O in the middle, and then I have 2 lone pairs on the O. Okay, and I'm gonna now erase the line because they're not bonds or lone pairs around that O. Now, when I look at my uh, my molecular geometry, I'm just now going to look at the atoms involved. So my H connected to the O, connected to the other H. That shape obviously is not tetrahedral. It's not a straight line. It's not a trigonal planar. It's not trigonal pyramidal. I just have those 2 things, 2 H's connected to the O in the middle. That is a bent shape for water. And it is very critical that water has that particular shape because, as you know, we find water everywhere. It's very important. And the fact that it's bent gives it some of its very important both physical and chemical characteristics. If we take a look at a couple other examples, so we've gone through now having 3 electron groups around the central atom, having 4 electron groups. As we start having 5 and more, right, we're going to have multiple options for shapes of these molecules. And all we're doing is we're going to be now replacing the the groups with lone pairs, and as we replace positions with lone pairs, the shapes of the molecule will no longer correspond to the shapes of the electron group geometry. So let's take a look at a couple examples, and we're going to illustrate this using, let's do, we'll do another example. Let's do, we'll do SF4. Okay, so sulfur tetrafluoride. Okay, first step to determining molecular shape is to now draw the Lewis structure for this. Okay, so following our rules for Lewis structures, we're going to see that the sulfur is going to have those four fluorines around it, and then we're also going to have something additional. Okay, so let's do our electron count, our valence electron count. We have one sulfur, sulfur's in group 6. We have 4 fluorines, fluorines in group 7 times 4 is 28, plus 6 is 34 valence electrons, right? Sulfur is going to be in the middle. I have 4 fluorines around, 1, 2, 3, 4. I connect them all. I give my outer atoms enough electrons to account for their octet. So each fluorine needs 6. Okay, so I count my electrons. I have 8 and 8, 16. And 8 is 24. And 8 is 32. I need to have 34, so I have 2 electrons remaining. The only place to put them would be on that S. Okay, so remember, sulfur is one of those that can form an expanded octet. It's an exception to the octet rule. So that's a viable Lewis structure for SF4. The next thing we need to do now, once we have a Lewis structure, focus on the central atom, sulfur. How many electron groups are around it? Well, we have 1, 2, 3, 4, and 5. Okay, so we have number of electron groups. And again, we're just looking at around the central atom, which is sulfur in this case, is 5. And according to the VSEPR model, that electron group geometry will be trigonal bipyramidal. So I can spell bipyramidal. So if I were to draw that electron group geometry, it's going to look something like this. So I have my sulfur, and in the trigonal bipyramid, I have my axial positions, which are sort of like the north and south pole, and then I have my equatorial positions that are sort of around along the equator, right? So if you can imagine, if this were a globe, like so, right? This is the equator that kind of goes around like so, and then you have your North Pole and your South Pole, right? That's the way to visualize the positions in the trigonal bipyramidal structure. So I'm going to erase that because it becomes a little cumbersome. Okay, so I have now my SF4. I have my electron geometry being trigonal bipyramidal. I'm going to stick in now those atoms and the lone pair. So I have a choice of where to put the lone pair. Okay, so the lone pair position, that's the only thing that's different than all the other electron groups, right? All the other electron groups are single bonds. Yeah, 4 single bonds. And then we have this lone pair. So where should I put the lone pair? Because the axial positions are different than the equatorial positions. Well, because the lone pair occupies a bigger space, you can think of the lone pairs occupying a larger volume than a bonding pair. Of electrons, it will want to go where there's more room. Okay, and if you can remember, along the equatorial positions, there's actually a bond angle here of 120 degrees between the positions in the equator or the equatorial positions versus 90 degrees between the axial and the equatorial positions. So if we have a choice of where to put the lone pair in a trigonal bipyramid, we're going to stick it in one of the equatorial positions because there is more room in that location. So the equatorial positions have more room. And that's where the lone pair will want to go. So I'm going to put my lone pair right there. Okay, I'm going to erase that bond because it's not a bond to the lone pair. It's just a lone pair. And now I can put my Fs in. Okay, so I have an F up here, 2, 3, and then 4. So I've used the electron group geometry to have my basis, my foundation, and then I decide where that lone pair is going to go. I put it where there's the most room available, which in the trigonal bipyramid is along the equator. And now what I can do is look at the shape of the molecule, right? So the molecular shape now, I'm just looking at the atoms and see how they are connected. And this is where visualization, how you interpret something in your brain, is going to be very helpful. It's going to be useful. You're probably going to have an exercise in the lab also where you build these molecules. So let's take a look. I see my sulfurs in the middle. I have 2 fluorines that are sort of opposite to each other, top and bottom. And then you can think of these Fs here as sort of like making a sort of an axis along the center. So if I take this structure that I just have drawn and I tilt it or I rotate it this way by 90 degrees to the left or counterclockwise, the shape that I end up with looks like this. I have my sulfur, 2 Fs on either side. There's my lone pair on the top. And then I have 2 Fs like so. This shape, if you can, again, imagine it in 3-dimension, this is called a seesaw shape. Right, and that's how the atoms are connected. These are the both sides of the seesaw where people would sit, and the bottom portions here, this is where the middle of the seesaw is, where it can rotate, and that's the center of rotation essentially of the seesaw. Right, so that shape is actually the molecular shape here is the seesaw shape, right? And you'll see this on your table that you have in your textbook. Right, so you have your 5 electron domains, 1 lone pair. So one of those positions being a lone pair, that shape, then the molecular geometry becomes the seesaw. If we had a second lone pair in that, out of the total electron domains, that second lone pair will also occupy an equatorial position. And in this case now, the shape would look like a T, and we call it a T-shaped position. If we had a third lone pair, again, it will occupy that equatorial position. So now this position here becomes a lone pair. Well, then what remains, the atoms remain just there in a straight line, and it could be linear, right? So you can have a linear shape resulting from an electron domain geometry of trigonal bipyramid. We can also have linear arrangements or linear shapes just by having 2 atoms and 2 electron domains around the central atom as well. As we go on to 6 electron group geometries, well, then the shape becomes they become a little different also. Okay, so now that we've have an idea of how to approach predicting the molecular geometry based on the electron group geometry, what we're going to see is that once we start introducing, especially lone pairs around that central atom, and lone pairs around in the molecule or in the ion, for instance, they will now cause the ideal bond angles to be slightly different, or in some cases, moderately different than what is predicted. And a good example, we'll see some examples here of this. And again, this is now relative to the central atom. So not relative, but around the central atom is what we're looking at. And we're going to see the following. If we have lone pairs around the central atom, we've already talked about the fact that they take up more space than bonded pairs of electrons. So if they're occupying more space, right, that means other things will have to occupy less space, and they will make the bond angles different. What we also find is that if there are multiple bonds, so things like double or triple bonds around that central atom, they will repel the other bonds more strongly than single bonds would. All right. So let's take a look at some examples here. We had the structure of ammonia that we drew before. Okay. And we saw that ammonia, NH3 has a total of 1, 2, 3, 4 electron groups around it. And those electron group geometry will be tetrahedral. Okay, and if you recall, the bond angle in a tetrahedron is 109.5 degrees. That's the ideal bond angle. However, in the case of ammonia, okay, that bond angle between the NH bond and another NH bond is not 109.5. It is actually less than, right? It's 107. So this is less than the ideal bond angle. And why is that? Well, this is because on top of the nitrogen, there's a lone pair of electrons. And what this does is it actually pushes down, it repels, it takes up more space, right? Think of the lone pairs occupying this huge volume up here, and it repels, it pushes down on these bonding pairs of electrons. It actually, in essence, it squeezes the bonding electrons together. So the bonding pairs of electrons closer together. And as a result, right, the bond angles now become a little bit less than the ideal 109.5. Okay, so it still is fairly close, but it is less because of the space taken up by the lone pair. Same thing happens in the case of SF4 that we looked at. Okay, this lone pair of electrons around the sulfur takes up a huge space. It is going to press down, it's going to repel the bonds around it. So normally this bond angle here between this SF bond and this other one, that bond angle is ideally 180 degrees. Okay, that's the ideal bond angle, right? We find that it's not, it's actually squeezed in a little bit. It's 107, I'm sorry, 173.1. What we also find is that this lone pair, it actually squeezes these SF bonds here closer to each other as well. So instead of this being the ideal 120 degrees, right, they're now squeezed together to be about 101.5, right? So that's a fairly sizable squeeze that's happening between the sort of the fulcrum of the seesaw. And then similarly, in the case of an octahedral electron geometry, so we have here this lone pair that's taken up a big, huge space. It is going to now squeeze, it's pressing down on these, it's squeezing these together. Ideally, right, this bond angle here is 90 degrees. Ideally, this bond angle here is also 90 degrees. Let me draw it a little bit better. Ideally, that's 90. Ideally, this is 90 as well. Ideally, this is 90. So they're all 90 in the octahedron. It's the presence of this lone pair squeezes those bonds to now they become less than 90, about 85 degrees. What we also find is that in addition to the lone pair around the central atom, taking up a lot of space, making bond angles less than ideal, we also find that double bonds, multiple bonds, so this is a double bond. Okay, this can now squeeze, it can repel these single bonds a lot more strongly, and it can make the bond angle now between these two bonds here, it can squeeze them together and make the bond angle less, right? So ideally, in this trigonal, this is a trigonal planar arrangement, right? Ideally, the bond angle here is 120 all the way around. In this case, the double bond squeezes these the bonds in yellow, it squeezes those together. So this 120 degrees here becomes less than, so it goes down to 116. But if the bonds in yellow are being squeezed together, what that means is that the bond angle here in pink, that actually will go up, right? Because now you're making the angle on the other side smaller. This has to go up as well. It goes up to about 122. So we have deviations from ideal bond angles due to having lone pairs around the central atom or having multiple bonds around that central atom. We will also run into situations where there may be more than one central atom in a molecule. And in that case, we're just going to look at the geometry around each of those individual central atoms. So for instance, in the case of this is methanol, a molecule called methanol. We don't have one central atom here. We actually have two. We have the carbon, okay, and then we also have an oxygen in yellow. Okay, so in this case, we look at each of these individually. And we do the same thing. Okay, so if we look at the carbon first, around this carbon here, we have 1, 2, 3, 4 electron groups. All of those are bonded to atoms, so that will be tetrahedral. Both the electron geometry and the molecular geometry. Around the oxygen here in the yellow, again, we have one. Around the O, we have 1, 2, 3, 4. So the electron geometry will be tetrahedral, but around the O, we only have 2 atoms connected, the H and a C. So the shape around the O then, the molecular geometry around the O, will actually be bent. Okay, so we're applying the same rules, but now we're separating the molecule out into these two different regions. One region has a central O, one has a central carbon, and we're looking at those individually. What this also means is that the shape, the bond angles around each of the atoms in here will be different. So for instance, right, if I look at the bond angles around the carbon, because that's tetrahedral, right, and there isn't a lone pair around the carbon here, we can assume that these bond angles here are all going to be the tetrahedral bond angles, which are 109.5 degrees. And then around the oxygen, right, again, we have the tetrahedral electron group geometry around the O. We can now assume then, because two of the tetrahedral positions are taken up by lone pairs, right, we can assume then that the bond angle between the OC and the OH bond, that's not going to be 109.5, right, because we have 2 lone pairs now occupying positions in the tetrahedron. We can say this bond angle here is going to be less than 109.5. Okay, because the shape around there is that bent shape. Okay, so even though your Lewis structure kind of looks like a straight line, okay, it's definitely not a straight line that we have in the structure.